be encouraged to ask questions. Well, there we go. We're starting it. To ask questions, or if someone else has the same question, we won't duplicate too much. And then finally, at the bottom, you can see our code of conduct. We ask that you are a respectful person as you participate in this event. So I guess without further ado, Janine, you can stop sharing and we'll turn it over to Ralph. So welcome. Oh, I'm sorry. Did we go through Ralph's bio? I think I might have missed that one. My bad.
It's okay. I have an intro slide if
You do? Okay, great.
yeah,
So yes,
we
please
get to
tell us
that.
about yourself. We'd love to hear that. Okay, so you know what? Janine's got it up. I'll go through it. So Ralph sent this information to me. He is the founder of a data-driven supply chain. That is a Minnesota-based consultancy. So it applies data science, other methods, including linear optimization, to evaluate, design, and optimize client supply chains. So he has also a lot of experience in operations research, working at companies such as Target and General Mills. So if you're interested in learning more or talking with Ralph about a consultancy option, please reach out to him at the email address below. So, okay, now take two without further ado. We'll kick it off to Ralph.
All right, thank you. Share and hopefully get this right. Okay, do y'all see the PowerPoint? Okay, get some thumbs up. Thank you. All right. So yeah, thank you for the opportunity to speak to this group. I love talking about linear optimization and operations research, and I love working in R. So this seems like a really great time to share what I think is a very powerful analytical technique, but it's really not as well known as I think it should be. And so really appreciate the opportunity to speak to this group about it. So as mentioned, my name is Ralph Asher. I'm a operations research scientist, which is another way of saying a math guy, and live here in Minneapolis, where I worked in the corporate world for about 8 years before hanging out my own shingle a couple of years ago. And like to say that ever since I was a kid, I liked math, I like maps, and I like programming. And I managed to find a job that matches all three of those and works in concert. So very fortunate about that. All right. So what is optimization modeling? Basically, optimization modeling is a mathematical technique that allows a practitioner or an analyst to optimize a set of interconnected decisions where the decisions are constrained by real-world limitations. So what do I mean by interconnected decisions? Well, every day you face interconnected decisions. If you spend money on going to the movies, you don't have those dollars to spend them going out to eat. If you spend your time watching television, you don't have that time to go, to a museum or go to the gym or whatever, right? You have interconnected decisions around fixed resources, whether it be time or money. And so when you think about real world business decisions, most business decisions are interconnected and there's trade-offs. And optimization modeling is a way to take those trade-offs into consideration and make the set of interconnected decisions that optimizes, meaning minimizes or maximizes some value that you care about. And so when you build an optimization model, you take all these interconnected decisions, put them into variables, define inequalities that show the relationship between these variables, and then send them to a special software called a solver. And another term for optimization modeling is called mathematical programming. I don't like to use the term mathematical programming, even though it's the official term, because programming means something fundamentally different than it did back in the 1940s when this was coined. And also, by the way, feel free to raise your hand with any questions. I can either answer or might defer them, but if you have questions as we go along, I'd be happy to hear them. Okay, so in an optimization model, there's something called decision variables. So a modeler will define these decision variables, and these are just numeric variables that either directly represent the decisions that you want to make, for example, the dollars you spend at the movie theater versus a restaurant, or many decision variables facilitate constraints, limitations on your decisions. In your model, there is another mathematical expression called the objective function. And an objective function is a mathematical expression, not an equality or an inequality, just an expression, that represents the thing you want to minimize or maximize. So for example, maybe every dollar you spend at the movie theater gives some enjoyment in life, some utils for economists. Going out to dinner might offer a different number of utils. Maybe you want to maximize the total number of utils you can acquire. In most business decisions, usually the objective function is related to the cost or the profit associated with a set of decisions. And we'll see that here in an example here in a little bit. Now, once you build this objective function and these constraints, the optimization model is then sent to specialized software, and it's called a solver. And the solver will do some very complex math that I won't go into today. And the solver will then determine the value of all the decision variables that yield the optimal value of the objective function. Your decision variables, which again represent your real life decisions, can be three main types. One is continuous, that's any real value, and usually there's an upper or lower bound to those. So for example, the amount of money you spend at a restaurant has a lower bound of 0. So if that's a decision variable, it's not going to be below 0, and potentially it could be as high as your credit card can allow. Decision variables can also be integers, which are just any integer value, possibly within a bound. And they could be binary, more restricted than integer, and they can only take a 0 or 1 value. Sometimes people ask, well, why do you have binary decision variables if you also have integer variables, since 0 and 1 are integers? Well, 0 and 1, of course, if you're familiar with the history of computer science, 0, 1 represents on off of a switch. 0, 1, very good at representing yes or no decisions in a business. So for example, if I'm going to open a warehouse in a supply chain context, that could be a 0 for no, a 1 for yes. So that's where binary decision variables usually come into place, is those big yes no decisions. All right, so the types of decision variables and the form of the constraints, those limiting factors in your decisions, and the objective function, the form of all those will determine what type of optimization model you have. So the first one is called a linear programming, or an LP model. And that is an optimization model which has only continuous decision variables. So all the decision variables are any reals bounded by the upper and lower bounds. And all constraints and the objective function are linear expressions. And I'll detail a little bit more about differentiating between linear and nonlinear in a moment. A mixed integer linear programming model, or an MILP, is a linear programming model where at least one of the decision variables is a binary decision variable or an integer decision variable. And then all the constraints and the objective function are linear. So the only difference between a linear programming model and a mixed integer linear programming model is the presence of at least one binary or integer decision variable. Finally, we have nonlinear programming, or NLP, which is one of those acronyms, which of course means something else if you're in the in data science, but in optimization model, it means nonlinear programming. That's where at least one term in the constraints to the objective function is a nonlinear term. So for example, two decision variables multiplied by each other makes it nonlinear. So in supply chain modeling and most optimization modeling, really, mixed integer linear programming is the dominant form of optimization modeling. In finance, there's a lot more applications around nonlinear, but for the work I do, it's almost exclusively linear and mixed integer linear. Tonight, we'll cover a couple examples of linear programming, and if time allows, we'll get into a mixed integer linear program as well. And again, if you have questions as you go along, I've probably built in more than enough time, so feel free to raise your hand. Okay, so just as a quick overview when I say a linear expression or a nonlinear expression. A linear expression is an expression that makes a straight line in one or more dimensions when you replace any inequalities with an equality. So for example, x plus y equals 7 in the xy plane generates a line. X less than or equal to 3, if you replace the inequality with an equality, that generates a line, x equals 3. X plus y minus 7, or sorry, x plus y minus z equals 10, generates a or generates a line in 3D space. These all generate lines. So that's a linear expression. More generally, a linear expression can be rearranged to the form of all variables multiplied by a constant equals a constant, whether that constant be 0 or non-zero. So just generally, that's the form of a linear expression. A nonlinear expression is pretty much anything else. So if you were to plot it in multiple dimensions, yes, we'll post the PowerPoint at the end. Thank you for asking. And so, for example, x squared equals 7. You plot that, definitely not a line. Definitely not a line. Absolute value, not a line. Multiplying two decision variables together, minus another one equals 5, not a line. So a lot of examples of things, if you use, for example, trigonometric functions, that's another big one. All those things are nonlinear, and that makes optimization modeling a whole lot harder. Life is much, much easier when everything's linear, so that's why we try to keep that way. And so the presence of any nonlinear expression in the constraints or the objective function of an optimization model makes it nonlinear. One bad apple ruins the bunch as far as that goes. So there's a lot of modeling tricks that have been developed to make things that look like they should be nonlinear and actually make them into a linear form, so you can make a linear model out of them. And that's a pretty large part of my searching Stack Overflow is trying to figure those tricks out, actually. Okay, so give an example. A modeler will define decision variables. Remember, decision variables either directly represent the decisions you want to make or are generated to help facilitate constraints. And the objective function is an expression that we want to minimize or maximize. It consists of some or all decision variables. Doesn't have to include them all, but at least includes one, plus coefficients to those decision variables and or a constant. And as a reminder, a linear programming model only includes continuous decision variables, and all the constraints in the objective function are linear expressions. So we'll give, if we go into one example here in a second, and we will make some simplifying assumptions about the linearity of the real world for teaching purposes. So you'll pick up pretty quickly on where we're making the assumptions. All right, so as mentioned, I live in very cold Minnesota, so I live in the Minneapolis suburbs, and so this example is called the toy shop example. And if you take an introductory course in operations research, you'll see something like this. I had to customize it, of course, for Minnesota. So Northwoods Toy Emporium is the premier toy maker in Minnesota. The store makes and sells their own product, and they have only 2 items, very specialized, 2 items: wooden cars, wooden trains, and they hand make each one of them. So each of these 2 toys, the cars and the trains, have different costs associated with them and different resources that are required to make them. So to make one car requires 5 hours of woodwork and 1 unit of wood. Each train requires 3 hours of work and 1 unit of wood. Same amount of wood, different amount of time. The profit on each car is $7, and the profit on each train is $4. Now, the expert toy maker in the shop has 40 hours a week for making toys, and due to supply chain constraints, we only have 10 units of wood available each week. So knowing now that we have different profit, time, and wood requirements for both toys and trains, and we have a limited resource of time and wood, what's that mix that we should make? what are the wooden cars and how many wooden cars and trains should be produced each week in order to maximize the profit. Okay. So I'm going to give myself a break so I can sip some water and ask you, what in this problem for a linear program, we need 3 core inputs. We need to know what are the decisions we need to make, what are the constraints, and what is the objective. So in a business sense, what are these things so that we can then make it into a mathematical model? Feel free to either speak up or put it in the chat, please. Yep, so yeah, our limitations are 40 hours a week and 10 units of wood. Yep, that's our objective. Thank you, Robin. And thank you, Martin. All right, and what's our decisions? Yep, thank you, Mary. Okay, so we got it all. Yep, we need to decide how many toy cars to make, how many toy trains to make. We know our limitations on time. We know our limitations on raw materials, and we know how much of each of those resources, time and materials, each toy will take. So now we have a business problem. Now the question is, how do we translate this into a math problem that we can actually solve? Okay, so let's take what we just referred to and let's start to make it into some equations. So we're going to first take these decisions and assign variables to them. So number of cars we produce, we're going to call this continuous. This is where I said you got to suspend your disbelief a little bit, because we're going to say that it's possible to make like 2.3 cars instead of integer values here. And that has a lower bound of 0 because we aren't going to make negative cars. We can make 0, but we can't make negative cars. The number of cars we produce, we're going to call that X. Number of trains we produce, we're going to call that Y. That's our decision variables. Now our constraints, let's first look at the amount of hours we have. We have 40 hours and each car needs 5 hours. So 5 times the number of cars we make plus 3 hours per train times the number of trains we make has to be at most 40 hours. That's the constraint on the toy maker's time. And our supply, our wood, we need 1 piece of wood for each. So it's just 1 times number of cars plus 1 times number of trains is less than or equal to 10, the number of units of wood we had for the week. And our objective function is we want to maximize our profit, which is $7 times the number of cars we produced, plus $4 times the number of trains we produced. Okay. Okay, so now that we have this, we've gone entirely from a business problem to business logic. Now we have something resembling equations. Now let's make them into equations. Over here on the left is the slide you just saw. We're just going to transform it into a series of inequalities. So the number of cars is X, number of trains is Y. The woodworking constraint is now 5X plus 3Y less than or equal to 40. Our supply of wood is just X plus Y less than or equal to 10. And because we cannot produce negative cars or trains, we have to explicitly say X is greater than or equal to 0, Y is greater than or equal to 0. And our objective function is to maximize the expression 7X plus 4Y, in this case in dollars. Okay. Something that kind of takes a little bit of time to ingrate yourself in your mind if you're doing optimization regularly is to remember that computers can be really smart at things, but they can be really dumb at other things. And so when you are building an optimization model to reflect a business problem, I always like to think of it like I have a 3-year-old daughter and a 5-year-old daughter. And if they want to do something, they will take the letter of the law of what myself or my wife will tell them to do it. Like they will bend what you told them to do what they want to do. So I try to think like, hey, if this optimization model wants to do something that I didn't intend it to do, what would it do? And you need to explicitly state things like, you can't make a negative number of cars. So those are the kind of things that make common sense just from a business perspective or a real life perspective, but computers don't know that. So you have to make sure that you are thinking that through and including those kind of considerations. Okay, so this is a block text. I apologize. The relationship. Can you all hear and see me again?
Yes, thank you.
All right, I apologize for that. I'll write Comcast a sternly worded letter tomorrow. All right.
They didn't optimize something.
Yeah, I know. They're optimizing their profits. That's what they're doing, minimizing service level. Okay, so basically, once you have those constraints set up, the objective function guides the search for the value in the decision variables that are optimal. So you have that expression that reflects the profit. Now, the fact that you want to maximize it will now tell the solver what direction generally should I search for the values for those. So there's a term called the feasible region, and this is a very technical term. So feasible in this case does not exactly mean what we mean in English. The feasible region is the set of all possible decision variable values that satisfy all constraints. Your optimal solution must fall within this feasible region, otherwise one or more constraints are violated. And you can define constraints such that there is no feasible region, that it's impossible to find decision variables that satisfy all your constraints. And so if you do that, you've put your model in an impossible situation, and the technical term for that is infeasible. And if your model is infeasible, your computer will tell you, it'll be upset and it'll let you know. And if you can also do the other way, which is you can say that you can define your constraints such that one or more decision variables can just grow without end. So if I had, so effectively that your objective function can increase or decrease without limit. In this case, the model is unbounded, like there's no limitation on the value of your objective function, and your solver will also be upset with you and tell you, and it won't return a solution. So figuring out why your model is infeasible or why your model is unbounded is one of the joys of debugging optimization models if you work in this field for a while. Okay, so what does this feasible region look like? Instead of me just talking about it, we'll do this visually, and this is the nice thing about just having two decision variables. So I'm not going to bring the website up, but this is a great website called Transom. Basically, you type in equations and it'll visually show it. So we'll one by one add constraints here for this problem and see what this feasible region looks like. So first, I'm going to add the first constraint that x is greater than or equal to 0. Number of cars is greater than or equal to 0. So when you add that in, the feasible region is now this blue part. Everything x greater than or equal to 0. When you add in the second constraint that y, the number of trains, is greater than or equal to 0, our feasible region is no longer this area, it's now this area, just the I don't remember which quadrant it is, but the positive quadrant. It's been a while since I had to learn that. So anybody remembers that, bravo to you. All right. Now let's add in our first constraint around the woodworking hours, 5x plus 3y less than or equal to 40. When you do that, now the feasible region is this triangle. So all points along the perimeter and inside the interior of this triangle satisfy all three constraints. We still have one more, x plus y less than or equal to 10, our wood availability. When you add that in, it's this purple line. Now our feasible region is the points on the plane that satisfy all those inequalities. And it's this 1, 2, 3, 4, 5-sided polygon right here. Okay. So this is our feasible region. Every point along the both the edge and the interior will satisfy all our constraints, including the origin. It is feasible to produce nothing. Not a good idea, but it is feasible. Yes, I love this website, this Transom website. I found it when I was preparing this for some training I gave. Okay, so let's zoom in on this feasible region. That's what the corner points look like. And so all points inside the polygon, including the edges on the perimeter, satisfy all the constraints. So any point in here, you can throw a dart at your screen right now, and if it lands inside this polygon, it's a feasible solution. It will satisfy all the constraints. Not necessarily optimal, but it will satisfy them. But the question then is, how do we have a feasible region, that's good. Now, how do we actually find an optimal solution within the feasible region? And this is where solvers come in, basically. Okay, won't go into the math of it because it's really, really mind-bending, but in a linear program where all the decision variables are continuous, the optimal solution of the problem, whether you're looking at the minimal or maximal solution, the optimal solution will be found on a corner point. It will be found on a corner point. That was, I think it was Kramarker. There's a theorem around it. But anyway, so it makes it really easy then if your problem is purely linear, it makes it actually really easy to find a solution because the solver just basically needs to build that polygon, or it's called a polytope if it's in more than 2 dimensions, and just look at all the corners basically and just see which one's the best. And so in this case, our optimal objective value is $56, and that's found by producing 8 cars and 0 trains at $7 per car. That's a value of $56. Also notice our minimal value is 0, also a corner point. So if we had been wanting to minimize within those constraints, it would have been also on a corner point, but it would have been the origin. Okay. So won't ask what the objective values are associated with the other corner points. One nice thing about R that I love as software is that it is so flexible, and so you can do things like this to make visuals of the objective value. So for all the points inside this polygon, I just found the objective value, real quick calculation, and then colored it from red being lowest, green being highest. So over here in the corner, our optimal solution, bright green, $56. What do you notice? There's a lot of points, particularly along here, that look pretty green. They look pretty close to optimal. So there could have been a lot of solutions that are not the highest, right? They're lower than $56, but are pretty close. And that's something that in optimization modeling, you should be aware of, is that oftentimes there are solutions that are very, very close to the optimal solution that may actually be just as acceptable or even more acceptable from a business perspective. Any questions thus far? All right, well then I guess we'll start going into our our example of actually how to program one of these. So there's a few different R packages that can be used for linear optimization. I love OMPR, and so it's the one I teach and it's one I use pretty much every day for my work. OMPR stands for Optimization Modeling Package for R, and it's authored by a guy named Dirk Schumacher, and he saw a gap in the ability to do linear optimization in R, and so he basically just built his own package, and so now I use it. And it's on CRAN, and it allows a modeler to build flexible linear programming and mixed integer linear programs models in R. Takes advantage of all the great things about working in tidyverse for data prep, and excuse me, and so OMPR allows you to build these models and then connect to solvers. So solvers are kind of like, maybe not easy to make an analogy, but solvers are separate from the modeling language. There are some solvers that are really expensive and commercial, like Gurobi. There are solvers that are free and open source, like GLPK, which we'll use today. OMPR works with a lot of different solvers, and you can just make your model in a standard way and then send it to whatever solver you want. So the general workflow for a project with optimization modeling in R is use R for whatever data prep that is, data munging, any kind of statistical analysis, whatever you need to do. Use OMPR to build the optimization model. And then with one line at the end, you send it to whatever solver you want. It solves in whatever time it does. And then OMPR pulls the solution back, and then you do some post-processing of the results to use them. So that's the general workflow. Okay, I'll go very briefly through these. These are the because I'll talk through them as we go through the Markdown document. These are the primary functions within OMPR, and they pretty much relate to the components of building an optimization model. So first, you instantiate a model using the command MIP model for mixed integer programming model. And then you add variables with the add variable function. You add constraints to add constraints, and you can call, for example, with add variables, if you have several different variables, you can call that as many times as you need. If you have a lot of different constraints, you call that as many times as you need. And then set objective generates the objective function. Again, the objective function is that expression that the solver will try to minimize or maximize. Set bounds, sets bounds on a variable. I've actually never used that. And then solve model pretty much tells the solver, take it and solve it. And then get solution pulls the solution back from the model to post-process it within your R script. Okay. I'm not going to go into too much detail about this because this is more syntax about each of those, but you can afterwards if you want to read it for context. We'll go a little bit more into it on the markdowns as well. Okay, and with that, we'll do our first markdown. So in the GitHub, for the GitHub repo for the presentation, it should have 3 markdown files. Open this one called session 2, exercise 1 toy shop. If you didn't have a chance to install all those packages, you just watch, but otherwise you can feel free to go along as you will, as I'm doing it as well. Okay. Okay, and you all see our studio now. All right, got some thumbs up. Thank you. I see yes, but very tiny. Okay. See if I can try to make it a little bit bigger. There we go. Hopefully that helps a little bit. Okay. So the first chunk, just load the relevant packages. So OMPR. OMPR.ROI is a helper package that basically allows OMPR, the modeling package, to talk to the solvers. So you need to do that. And then each solver that you use has its own package, and the format is ROI.plugin.solver name. In this case, it's GLPK, which is a free and open source one. All right, warning. I almost always start by cleaning my workspace. That may or may not be disastrous for your current workflow, so please be careful about that. I run that. This is always the part of the presentations where you never know if it's actually going to work. So hopefully things are working out well. Hopefully got the bugs behind me with the internet outage. Okay. So first I'm going to talk through we're going to build the toy shop LP example. So it might actually be useful to do a side-by-side here, if I can get it going. Okay, so remember, this is our linear programming model over on the right-hand side of our toy shop example. So now I'm going to show how you actually make it in OMPR. So first, we instantiate a model with the command MIP model, and then it uses pipes, pretty much just pipe in every component of your model. So when I make MIP model, it has nothing in it. I got to start adding things. I'm going to add a variable. What is it called? It's called X. What type is it? It's a continuous variable. And LB stands for lower bound, 0. So I'm going to create this decision variable X, and it has a lower bound of 0. There's also, if I wanted an upper bound, I could say UB equals whatever, but gotta make sure to tell it that I can not create negative toys. Then pipe, add variable Y, type continuous, lower bound of 0. So now I have a model with 2 decision variables, X and Y. I've explicitly said they have to be greater than or equal to 0. So now I have 2 constraints. One's around my woodworking hours. The other is the amount of wood. Okay, and just double check. Is this easier to see now? I know it's kind of busy on the screen, but hopefully y'all can see on my screen if you don't have it up on your computer. Okay, thank you, Mary. Thank you, Janie. All right, so I'm going to add the constraint, and my woodworking constraint is 5x plus 3y less than or equal to 40. Michael, that is not a naive question. That's the suspension of disbelief that I requested of you. Yeah, and that's where we'll get into that here in a moment. But yeah, for an introductory example, you always you start with linear because it is easier to explain visually both what's happening, like we did with the with that build-up drawing, and then also mathematically what's happening. But yeah, in real life, yeah, we can't make a partial number of toys. And so your first constraint is your woodworking hours, and just 5 times x plus 3 times y less than or equal to 40. Then our units of wood, x plus y less than or equal to 10. Okay. And then we're going to set our objective. Our objective function is 7x plus 4y, which represents the profit associated with each of our production values. And so set objective, there's the expression. In cents, just means do you want to maximize or minimize? So max or min. So I will just do Control Enter, and now I've generated an object called a toy model. So what does that actually look like if I look at it in the command line? Okay. It gives me a summary. It says I have a problem next to a linear program model. And how many variables? I have 2 continuous variables, no integer variables, no binary variables. Good, that's what I was hoping for. I want to maximize it, and it has 2 constraints. right on. That's exactly what I wanted. You can look at each of these components in more depth if you need to inspect it, but just from overview of what the command line gave me, looks right. Okay. So next, we have a model, but we haven't solved it. All we have is basically an object in R that represents our business problem. We don't have a solution. So now we have this solve model command, function, and I'm going to solve the model toy model, and with ROI and GLPK is our solver. That's just the syntax of it. So Control Enter, and it takes no time at all. The solution is now stored as the object of my solution. So if I look at what my solution is in the command line, it'll say success, meaning it's solved, and the objective function is 56. Doesn't tell you the values, but it says it completed. And our objective value of $56 is what we found when we looked at the corner points. Right. So that's given me some hope that that the solver did it right. Now we have our solution stored as my solution, and now you have to extract the values of the decision variables from that solution. In a larger integer program or mixed integer program, you actually may only care about a certain subset of the decision variables and actually want to get those values. So you don't have to extract everything. So I'm going to say get solution. From my solution, I want to get the solution value for X. I'm going to store that as X solution. For Y, call that Y solution. Okay. Okay, so optimal value of their objective function was $56, and the optimal value was X of 8, so 8 cars, Y of 0, 0 trains. Okay. If we plug that back in to our objective value, comes out with 56. So both our objective value that we calculated and the objective value that our solution returned was 56. That matches as we should expect. All right, so we just did the toy shop in OMPR. What questions before we do anything more, a little bit more complex and build on it? All right, okay. All right, so we're going to talk about how do we actually scale this, right? So it's all well and good to have 2 decision variables and we explicitly call them out as X and Y. Well, in real life, problems with these, you're oftentimes dealing with thousands or hundreds of thousands or millions of decision variables. If I had to hand type out every one of a 2 million decision variable problem, I'd probably never finish the project and my hands would hurt. So how do you actually scale that within an indexing framework like R provides, as well as Python? So in OMPR, decision variables can be declared as vectors. They don't have to be declared explicitly like X and Y. They can be declared as vectors. And so instead of using X as the decision variable for the number of toy cars and Y as the decision variable for toy trains, we can actually just build a model with a single declared decision variable just called toys, and we have 2 indices to it. And we know that the first index refers to cars and the second index refers to trains. We'll also now have numeric vectors that represent the time required for each toy, the wood required for each toy, and the profit associated with each toy. And so in a real world optimization model, this is how you do it. You basically index all your decision the first value of toy type is car, and the first value of time required is train, sorry, my internet connection is unstable again. So first toy type is car, and in time required, the first value is 5, which is the time required for cars. Each cars and trains both need one piece of wood, and then a car generates $7 of profit. So the first toy in toy type is car, and then the first values represent the cars in the time, wood, and profit. Same for trains. Okay. So now what we can do is we only need to actually use add variable, call this function once. Instead of twice, we can just call it once and have it refer to all of our toys. And so our variable is called toy, index I is indexed from 1 to 2 because we have 2 toys. Type is continuous with a lower bound of 0. And now can introduce what's called sum expression. So think of this sum underscore expr sum expression. It's kind of like matrix multiplication, or a dot product actually is the most accurate term. So if you're familiar with the dot products in linear algebra, 2 matrices, multiply them on top of each other, element by element multiplication, take the sum of that. That's a dot product. So what we're doing here is we're saying that multiply our decision variable of the number of toys to make times the vector of the time required, take the dot product of those two. The dot product of how many toys we make and how much time they require, the dot product of that is our total time that we're using. And that's less than or equal to 40 hours, our work time constraint. Then we can do the same thing with our wood required. And that's less than or equal to 10, the number of units we have. And then our objective function is just the dot product of number of toys times profit. Okay. Taking more time reading my comments than it is actually building the model. All right. So when we call this up, we want to look at the contents of our model. It's exactly the same as it was before. 2 continuous variables, no others, 2 constraints, and we want to maximize it. But now we did this in 1 fewer line of code by indexing. We get that objective value 56 as we would hope. And we're going to get the solution, but now instead of having to get the solution separately for cars and trains, we're just going to get it by calling the solution for our decision variable twice. Okay. We look at this, what does it say? It says our variable is toys. It gives our index, and then it gives our value. It doesn't tell us what are cars and what are trains. So now we need to post-process these results to convert it back into the business problem we care about. And it's pretty simple because we're all indexed on we have the same order of indexing, so we can just refer to our toy type vector and add a new column there. So now we have the original solution with the first 3 columns, and now the value or the actual toy type that we're referring to. That before we expand it even more. Yeah. All right, so we just went from declaring each decision variable separately to declaring a group of decision variables, toys, Now you can see now how vectors can be used in declaring decision variables, setting constraints and setting objectives. So now let's expand on this. You can actually do all your data prep in R to build data frames or tables as basically preparatory data sets, and then refer to those data sets separately, refer to those data sets in an optimization model. So you don't have to necessarily generate the vectors individually. You can refer to a data frame. And that's what we're going to do now. So in this next section, we're going to expand out our selection to more toys. And I'm going to make this data frame called Toy Shop DF. Okay. So we now have 4 types of toys. We've included trucks and airplanes. And the trucks and the airplanes require a little bit more wood. And their profits are a little bit different. So now we have a data frame that represents all of our decisions and the benefits and costs associated with them in our toy shop. And now that we've done this, we now have a data set, and you can have whatever data prep you need to in advance in a real life business problem to do this. Now we have a set of decisions, and we can say, well, how many toys are there? Just take the number of rows of that data set. We know we have 4 toy types. So now, instead of having to say index from 1 to 2 or 1 to 4, we can just refer to the number of rows in that data set, that data frame. And this model here is nearly identical to the one we just saw, but now we're referring to a data frame instead of individual vectors. So we're going to add variable of toys I is indexed from 1 to toy type count, which we just declared as 4. We're going to add the constraint that the dot product of the number of toys times the column time required. We add all that up, take the dot product, that's less than 40 hours, less than or equal to. And then the constraint number of toys times the wood required, the dot product of that is less than or equal to 10. And the objective function, dot product of the number of toys times the column profit. And that's, and I gotta do sense max. And that's how we do it. So even though now we went from 2 toys to 4 toys, we have no more code. It's the same amount of code, same number of lines. If we had 1,000 types of toys, we'd still have the same 4 lines, as long as we had a data frame that's reflective of it. And that's where it's really beneficial to do optimization modeling within the context of our Python, where you can generate things like data frames to use as inputs. All right, so whoops, I'm gonna actually run it. Okay, so 4 continuous variables. As we would hope, we want to maximize. We have 2 constraints. Now we're going to solve it. And again, it solves very quickly. All right, the objective value is 57.5. So we just went from maximum of 56 bucks to 57.5. So $1.50 in our pocket. All right, what does that look like? What are the actual values of it? We need to get solution and then refer to our input data frame to get the name of it. Okay. All right, so here's our solution. This is the production plan that will generate maximum profits. What does anybody notice about this plan? Yep, can't make 2.5 airplanes. Yep. And that's where, in certain cases, using a linear program does not make sense. If we actually were doing this for a real business, you would make these integer decision variables instead of linear. Right. And that, with an hour, that is the first exercise. So we'll go back. Any questions on these? Otherwise, I'll resume the PowerPoint.
Do we want to take a 5 to 10 minute break? Janine, Mary, Shelley, thoughts about that?
Sounds good to me.
Yeah, small break would be it.
Yeah, let's see what time is it right now. It is 7:02. How about 7:10? Split the difference, 8 minutes.
Perfect.
Okay, so we'll regroup at 7:10.
Kansas City needs 7 and Memphis needs 9. So different demands by customer. Each supplier has the same capacity, so each one of them can ship up to 20 widgets. Now, remember in the transportation problem here, every customer needs to get their full demand, but not every supplier needs to ship their full amount. And so if you add up the demands, we have 30, 37, 46, 46 units of demand, 60 units of supply. So we're not going to have, there's going to be some suppliers that aren't shipping everything. Our decision variable is how much to ship from each supplier to each customer. So pretty much how do we fill in this grid of number of units to ship from each origin to each destination. Now, the reason why I asked you to install Leaflet, the Leaflet package for this, is because Leaflet, if you are not familiar with it, is an awesome package that actually I think Posit maintains it, but it's great for mapping. I use it all the time. And you can make a quick map like this in literally 3 lines of code. So red are our suppliers, Chicago, Los Angeles, New York. Greens are customers in the Heartland. Apologize if you have to do some quick metric to imperial conversion. I actually did this for a European company, so I did it in. I didn't know anything about European geography, but I knew they probably would appreciate kilometers. So that's where that's at. So our objective function is basically going to multiply this distance from origin to destination by how many units we're sending from each, and then try to minimize the sum of all that. Okay. And with that, we'll go back into Markdown. So do a setup here, and okay. First, we're going to do some quick setup of data frames that represent our suppliers and our customers. And if I was doing like a real project like this would be, working primarily with the client's data to build this. But here we'll just basically do it by hand. Oops, that's not what I wanted. Okay. Latitude, longitude, and capacity of each of our suppliers. They have a capacity of 20. Latitude, longitude, demand of each of our customers. And this is that leaflet map that you just saw in the PowerPoint. Just made it with that 3 lines of code, well, 4 lines. And it's move it around. You can add pop-up labels if you want to, zoom in, whatever you need. Okay. Next, we need to create that distance matrix from each supplier to each customer, the one that you saw in the PowerPoint. So in doing so, we're going to utilize a package called Geosphere, which is awesome. It allows you to very quickly find the straight line distance between locations. Now, oftentimes in a real project, you're not using straight line, you're actually doing road distance, and you might call Google Maps API or something like that. But for here, we're just going to do it for, just going to do the straight line. And then we're going to use measurements to convert it from miles, or sorry, from meters, which is the original result, to kilometers. So the result is a matrix. Just add some row and column names here. So there we go. Yeah. So distance in kilometers from each of our suppliers to each of our customers. Okay. So now we have pretty much all the building blocks that we need to make a model. We have our demand, we have our supply, we have our distance matrix, which will go into the objective function, and we know our constraints. So here we go. Okay, this is going to get a little bit more complex than the previous ones, but we'll just go step by step. Okay. First, going to define a couple scalars, tell us how many suppliers and how many customers we have. We're going to use this for indexing. Okay, 3 suppliers, 4 customers. Okay. Step number 1, we are going to define our only variable, and we're going to call it flow. And this represents the number of widgets that goes from each supplier to each customer. And we're going to index it on 2 dimensions. Remember, with toys, we just indexed on 1 dimension, which was the types of toys. Here we're indexing on 2 dimensions, the suppliers and the customers. So I'm going to call these indices, supplier index, customer index, and say that I want to add a variable called flow, index supplier index from 1 to 3, and customer index from 1 to 4. These are all continuous with a lower bound of 0. So what does that mean? It means that now, once we do this, once we add this variable, we now have 12 decision variables reflecting the 12 potential origin to destination permutations we have here. And they're all continuous. We're just dealing with fractional widgets at this point, and they have a lower bound of 0. You can't send negative widgets. I'm going to stop my video real quick. Okay. Okay, so now once we've added that variable, now we're going to add constraints. So 2 types of constraints. 1, every customer's demand must be satisfied. So how do we do this? We indexing gets a little wonky here, or the syntax of it, so we'll walk through it. We have to add 4 different constraints, 1 for each customer. But we're going to do it with 1 line of code. So let's think of customer 1. Customer 1 is Dallas. If we were to add a constraint that just looked like what I have highlighted right now, we would say that the sum of the flow variables from all suppliers to customer 1, which is Dallas. So sum of that indexed along our suppliers equals customer demand, customer data frame, demand 1. What does that look like? That's 20. So this highlighted constraint says that the sum of all units that flow from suppliers to customers must equal 20, which is the demand for Dallas. That enforces that customer gets its demand. We then index this again over all customers. So when it actually looks like this, and not referring to 1, when we add this constraint, it adds that demand requirement for all 4 customers: Dallas, Denver, Kansas City, and Memphis. Okay, that was a lot. I know I talked about pretty much indexing across 2 different variables in 1 constraint. May not get all the syntax, but conceptually, are there any questions about how that works? All right. So that's an equality constraint that says they must equal. We now have our next constraint, which is that our supplier is limited by its capacity. So each supplier, New York, Los Angeles, and Chicago, can produce only 20 units. So we have to explicitly tell the model, you can't ship more than 20 units out of Los Angeles, no more than 20 out of Chicago or New York. So now instead of summing across suppliers, we're going to sum across customers and then index along suppliers. So we're to place this with ones. The way this would read is that the flow from which one is number one? The flow from supplier one, which is Chicago, to all customers. So flow from one to all customers, that sum is less than or equal to the capacity for supplier one, which is 20. Now here, all the suppliers have the same capacity. They don't have to. They could have, different numbers, and this constraint will work the same. So we do this for each supplier, and then, or you do this for Chicago, and then it repeats for the other two. So now we have our constraints. Each customer must receive its demand. Each supplier must stay within its capacity. And now we want to set our objective. So our objective function is demand times distance, the dot product of those two. And we want to just minimize that. So our objective function is just our decision variable times our supplier customer distance, which is a static matrix that we have. And we index across our two different decision variables, or sorry, our two dimensions, our suppliers and our customers. And then we want to minimize it. So everything I have highlighted here is just the dot product of our decision variables of how much product will flow times our distance matrix, which is a static object in the R workspace. And we want to minimize this in this case because we want to ship it from the closest place. And that is the model. So we're going to generate here. Let's look at it and see what it looks like, at least the overall capabilities of it. Okay, so variables, 12 continuous variables. That's what we were hoping for. 3 origins to 4 destinations, 12 decision variables. We want to minimize it, and there are 7 constraints. We have 4 constraints, 1 for each customer demand point, saying that its demand must be satisfied. And we have 3 constraints for each supplier, that it must be within its capacity, so 7 constraints. Okay, thankfully went as quick as I was hoping. And our objective value is 62,728. What does that represent? That represents the number of widget kilometers in the minimum transportation. So number of widgets along a lane times the number of kilometers, just like any other compound unit, it's a widget kilometer. And we're minimizing that by generally shipping from the closest location. When we retrieve the solution, what does the solution look like? It says our variables flow, and it just has by supplier index and customer index how much is transiting along that lane. Some of it's 0, some of it is more than 0, 7, 10, 3. But I don't off the top of my head know what supplier index 1 refers to or customer index 3 refers to. So I'm then going to refer to those input data frames that we set up. And now that looks a little bit easier to read. So we now know from the Chicago to Dallas flowed 10 units. From Los Angeles to Dallas, 10 units. From New York to Dallas, 0 units. Okay. So these are the raw outputs, and we've layered back in the context of the model. So remember, optimization models are dumb. they don't actually have any idea what real life circumstance you're trying to model. All they know are decision variable names, and there's no context associated with it. So you gotta kind of back out to then make it useful. Okay. So now we have a data frame, we have a table. What does that actually look like? So one thing you'll notice is there's a lot of 0 values here. It's good to know, but we don't need them. So I'm gonna just filter those out. And now flow solution is only the actual flows, the non-zero ones. And I'm gonna make a new map. It shows that. All right, so this is what it looks like. So I had to turn my video off. My computer was moving a little slow. So if you're all, I can't see any thumbs up or anything like that, but here's our map, and shows that Los Angeles is shipping to Denver and to Dallas. Chicago is shipping to Kansas City, Dallas, and Memphis, and then New York is only shipping to Memphis. Okay, what does this suggest to us? It shows that you can't necessarily just get everything from your closest location. It means that sometimes you're going to have to get from multiple locations. Like Dallas is closer to Chicago than it is from Los Angeles, but Dallas still had to get some product from Los Angeles. Okay. And if we were to take the results and put them back into that table, this is what it would look like. So when we look at these results, we see that both Chicago and Los Angeles are tapped out. They had a capacity of 20, and there's 20 units coming out of them as suppliers. New York, even though it had a capacity of 20, is only servicing 6 units, and that's to Memphis. Geographically, this kind of makes sense. New York is actually relatively isolated as a supplier compared to the demand base. When you look at Los Angeles, Chicago, they're much closer to the demand base. So the New York supplier is only coming in pretty much in a pinch when absolutely necessary. And we would have, it would look different if we had, different demand values or different capacity values for different locations, of course. All right. So that's it for the transportation problem. You all just sat through your lesson 101 on supply chain design. So if you have any questions, comments, anything like that, happy to share. I have one more thing around doing integer variables. It's just the toy shop, but with integers instead of continuous. But that's a kind of a smaller component of it. So if there's any questions or anything want to go into a little bit more at this point, I'd love to. And by the way, leaflet mini charts, one of the packages that I had on the list of things for this, that's what allows you to do these flow arrows. And leaflet mini charts allows a lot of other cool stuff. It allows you to do animation, which is really neat. It allows you to do like little bar plots on top of map dots, which is cool. Like you can animate them as well. It's a really useful package. Yeah, Jeanine. So leaflet is global. So you can, whatever locations you put into a data set and then feed it into the leaflet functions, it'll plot it. And so this is using OpenStreetMap by default, but there's a lot of other map services that you can call within leaflet. So there's if you look on RStudio or Posit, I guess, Posit's leaflet site, you can, there's maps to your heart's desire for whatever purposes you might need. There's some satellite ones too, which is good. I don't know the age of the satellites, but they're good to if you need imagery. Yeah. Yeah. Right. Okay, so talk briefly about integer variables then, and I guess that this will probably take maybe 5 minutes, and we can do any other questions. So why integer variables? So as brought up, you can't make 2.5 toy trucks. In general, the fewer integer or binary decision variables a problem has, the faster it will solve. Oftentimes, you can't get around having particularly binary variables because oftentimes a model has a lot of yes/no decisions that those binaries are good for. But sometimes you can't get out of it. If possible, you usually want to formulate your model entirely with continuous decision variables. However, there are many real world situations where a modeler must use integer or binary decision variables to effectively recommend decisions. Now, integer decision variables often are used in situations where the continuous variables don't make sense, like 2.5 airplanes. However, outside of kind of these smaller examples, it's actually usually pretty acceptable to use continuous decision variables to represent what are functionally discrete values. So let's say you're mass producing widgets, and an optimization model, you make a decision variable saying, hey, out of my plant in Minnesota, how many widgets should I produce? Well, you can make that a continuous decision variable, and the model might say, hey, you need to produce 714,229.33 widgets. Well, I can't produce a third of a widget. Well, it's acceptable to round that out, right? Because you're looking for a trade-off. Like the plan's not going to be significantly worse by rounding down a third of a widget, but your model will solve a lot faster if the number of widgets you produce is a continuous decision variable rather than an integer decision variable. But in other cases, rounding isn't acceptable. For example, with our toy shop, we're not mass producing toys, we're handcrafting them. And so doing that kind of fudging the results isn't going to work. Okay, so let's look at the cars and trains problems. Let's say that instead of our decision variables being continuous, we required them to be integers. Okay, this makes the problem a lot harder because before, this is our feasible region. And I color coded it by the objective function. Any of these values were okay, were acceptable. Any of these were feasible. But if you require integer values, only the dots, the integer values are acceptable. And suddenly, you're not necessarily going to be able to find the optimal solution easily. And it's probably deeper than can get into this call, but the math around integer variables becomes much more complex than the underlying math around a continuous decision variable. And so when you have an integer or a binary decision variable, I talked a while ago about how in a continuous, with continuous decision variables in a linear program, your optimal solution is always on a corner. That's a great thing that we can exploit to get a problem solved fast. When you have an integer variable, that's not true. The optimal solution might actually be deep inside that geometric shape that you can conjure in your mind. And how do you find it? Takes a lot harder, takes a lot longer. And so usually what optimization solvers do is they don't try to find the optimal integer solution or a solution that satisfies those integer constraints. They try to find a good enough solution. And you, as the analyst, decide what is good enough. So basically, I'm going to, if anybody doesn't know our background, forgive me. I know I'm going to butcher what actually happens here. But what the solvers do is first they find any feasible solution that satisfies all the constraints, including the integer requirements. They find what that objective function value is. And then they compare that to what would be the objective function value if those integer constraints weren't there at all. So if I was back to making fractional toys, what would be the best objective function value? Now I have to do integer value toys. So I have a objective function that is maybe the same, but it's certainly no better because we're looking at a smaller subset of our options. And so what is the gap? And basically solvers just say, hey, I have a gap. Is that gap acceptable? And it's expressed as a percentage. If that gap is under 5% or 1%, whatever you as the analyst specify, then it'll just say, okay, work's done, I'm gone. And it'll return that value. If it's not within that 5% gap that you specify, it'll keep searching for solutions until it finds one that is. Once it finds a solution that's within that gap, it's done for the day. It returns that value. So with mixed integer programs, any kind of optimization model that has an integer or a binary value, binary or integer decision variable, you actually rarely get the optimal solution. You get the good enough solution, and good enough is good enough because you might be literally waiting for the rest of your life for the optimal solution. So better use of your time. Okay. So just briefly show what that actually looks like here in the third one. Okay. And this is going to look exactly the same as our last toy model, with 4 types of toys. But now, instead of a continuous decision variable, we're going to specify it has to be an integer. Okay, so our toys have to be integers now. Okay. Okay. So now, when I look at toy model, I have 4 integer decision variables and no continuous decision variables. Want to maximize, and I have 2 constraints. Okay. So now, got to send it to a solver. I added this argument verbose equals true. Okay, so what this means is that now the solver will actually give you the gory details of what it's doing instead of just giving you the answer. And so you can see what's happening under the hood as we go along here. Okay, so thankfully it solves fast. So the message from the solver, it basically goes through a bunch of solutions until it closes that gap. Now here, I specifically said no gap, like you have to return the optimal solution no matter how long it takes. I did that because I knew it would be fast. And so the GLPK says integer optimization begins, and it goes searching through the potential options, and it found the optimal solution. That 0% represents a 0% gap. It found the optimal solution. And boom, integer optimal solution found. I'm done for the day. Here's your solution. $57. Okay. So remember when we were purely linear, our optimal solution was $57.5, $57.50. Here it's 57. Why? Because we reduced our number of options to just the integer options. Just like if you're searching for a house, if you're looking all across metropolitan St. Louis, you're going to have a lot more options than if you're looking for one particular suburb. So the fewer options you have, the fewer choices you have, and less likely you're going to get the thing that's perfect for you. So the more we're constrained, thus, by going into just the pure integers, the worse our options are, worse our best solution is going to be. What does that look like? It's 6 cars, 1 truck, and 1 airplane. Okay. And when our decision variables were continuous, the optimal solutions were 5 cars and 2.5 airplanes. So one thing that's interesting is that it's not just that the solutions are just a little bit different. They're actually quite a bit different, right? So we now went from having 2.5 airplanes to 1 airplane and 1 truck. It's not 2 airplanes in one truck, or 2 airplanes in 6 cars or 5 cars like it was before. The solutions might be actually quite different when you go from a continuous decision variables to integer decision variables. So, so yeah, that's the end of pretty much the presentation. I won't go into that. Binary variables, again, they're good for yes, no decisions. But yeah, I won't talk too much about that. And I see some other questions. So let's see. Yeah, okay, yeah, it's great question, Jane. Yeah, and that's absolutely true. The constraints are rarely so purely known. So there's a few ways you can do it. One way is to say that you can kind of repeat it over and over. So like you saw how quickly it solved. You can do that for 8 pieces of wood or 9 pieces or 15 or however many, whatever that range is. You can do that and solve that model for each of those individual constraint values and see how those plans might be similar or different. Especially if you have a model that solves as quickly as this, that's how generally modelers do it, is you just run all those scenarios and compare. There's other ways called fuzzy optimization, which is exactly that. It's fuzzy constraints. That gets the math, that gets a lot more complex on how you actually model it. Usually scenario modeling is how you approach those kind of things. And same things with like, hey, I don't know if I'm going to get exactly $7 in profit. Maybe I got to sell this one for $6.50. So maybe there's some questions around the objective function or the constraints as well.
Cool, thanks.
That's a great question. Thank you for asking.
Sure, yeah, this is my first introduction to this topic, so I'm thinking of all the possibilities. Any other questions for Ralph before we wrap it up for the evening before our big snowstorm here? We have Michael has a question. Feel free to put it in the chat or unmute yourself and ask whatever works best for you.
I unmuted, that might just work best. Can you have a situation where you have some constraints that are optional? So for example, you have 4 constraints, you have to have constraint 1, 2, but then either 3 or 4.
Yeah, that is possible. That gets kind of tricky in terms of how you actually model it, but it is possible to include those kind of things in. Yeah. And that does happen sometimes. There are certain business decisions where maybe you take one route versus the other. And if you take one route, certain set of constraints apply. If you take the other constraints apply.
Exactly, yeah.
And it is possible. It becomes a brain bender in terms of how you actually have to implement those on a case-by-case basis though. But it is possible.
Okay, it's not a one-on-one session.
Yeah.
Are
Okay.
there materials or at some place you would suggest Michael look to get started? Or no?
I mean, I have some grad school textbooks. Actually, OR Stack Exchange is actually pretty good. So there's an operations research Stack Exchange, and that's kind of place where if you want to learn more about the field as you get more into some of those more complex questions, it's a great place to ask. I've definitely consulted. It's great because it's like a lot of retired university professors just hang on there and answer questions all day. So it's excellent when you have questions.
Awesome, I can see my retirement path opening up. Anybody else? Oh, Audrey has something in the chat.
How do you get around a solve version? Can you clarify what you mean, Audrey, by saying making it an infinity?
Hey, this is Audrey, and I'm actually watching with my husband, and he was curious about this. I'm gonna let him speak.
Okay.
So yeah, when you have a solver that's constantly trying to make the objective variable larger and larger, it's not converging. Is there a way you evaluate your constraints that, you know, you just look at them and can kind of tell which one is causing that issue, or do you have a method to kind of eliminate things and make it converge?
Yeah, that's great. Okay, yeah, so the term of that is unbounded. If your objective function is
Yes,
unbounded,
yeah.
Usually it's like you miss something crazy. Like for example, if I forgot to say that I can not make that my number of toys is minimum of 0. Like if I forget to say that, it'll be unbounded potentially. And it'll tell you that. So usually unboundedness is a result of just kind of missing something fundamental. You just got to check your work until it doesn't happen. But if you cover that and it's still unbounded, it's a lot of guess and check. It's a lot of like, hey, I'm just gonna remove this part of my code and see if it works until I find which is the issue. Same thing with infeasibility. Sometimes 2 constraints, even if you don't intend it to, 2 constraints work at cross purposes to each other. In which case then it's detective work, more or less. Very dull detective work.
Got it. Yeah, thank you.
Thank you.
Thank you for asking.
Great. Anyone else? We have this expertise in the room. All right, well, I just want to, on behalf of Our Lady St. Louis and all the participants tonight, to thank Ralph for his time and his expertise. It was super clear, great introduction. So we really appreciate you kicking off our 2023 set of workshops with a great workshop. So thanks very much.
Thank you for inviting me, and anybody want to connect with me, either email me or find me on LinkedIn, happy to connect. Thank you.
All right. And our next one, you can find us on Meetup if you want to RSVP there. We've got 3 more coming up this spring. The next one is in late February. I can't remember the exact date, but it's on our Meetup and it'll be on our Twitter. And we've recorded this. I'm going to stop the recording. I just reminded myself.